Hey everyone, it's Dr. Walker. This is example number 2 from v045 on conservation of energy with friction. In this example, we have two masses that are connected. M1 is on a rough surface. We are given the coefficient of kinetic friction, and M2 is hanging. It says we are given the two masses, and the system is starting from rest. What is the speed of the ball when it has fallen distance h is 1.5 meters. So the ball is going to fall a distance h. That means that the box here is going to move that same distance h horizontally. We can identify this as a system that consists of the M1, M2, and the ground here, the earth. And we do have friction, that is a non-conservative force that is acting on this system, but we don't have any other additional forces. So if we only have friction that's acting and doing work, then we can use the equation that we just learned. Initial kinetic energy plus initial potential energy plus the work done by non-conservative force equals a final kinetic energy plus the final potential energy. What's new about this problem is that we have two masses. So when we're talking about kinetic and potential energies, we have to consider both masses. Let's start with the kinetic energy initial. It says that we're starting from rest, so we know that there's no kinetic energy initially. What about potential energy? There's no spring. We don't have to worry about a spring potential energy, but there is some height, so we're going to have some gravitational potential energy. Before we can figure that out, we have to figure out what's going to be our level y equals 0. You could make it the ground, or you could make it whatever height we have after we have fallen a distance h. The lowest point that we care about, we can set that equal to y equals 0. That way, after this ball has fallen a distance h, it won't have any gravitational potential energy relative to that point. Alright, so that being said, we know that M1 definitely has some height above this reference level here. But assuming that it's still on the tabletop after moving a distance h, we know that for the final situation here, it's still going to have the same exact height. So we can say that U1 initial, which is going to be M1G Y1 initial, is going to be the same as the M1G Y1 final. So we don't really care what that height is because those two energies are going to cancel out anyway. But let's look at mass 2 here. Initially, it's going to have potential energy equal to M2G Y2 initial. But what's the Y2 initial going to be? Well, relative to the y is equal to 0 point, that Y2 initial is just going to be a height h above that. So we can call it M2GH for the initial gravitational potential energy of mass 2. That takes care of our potential energies. And then we said that friction was going to do negative work. So let's do it on this side here. Let's find the work done by friction, which is going to be negative work. Negative FKD was our definition. So the friction force is negative mu n times d. Now we know that the friction is only acting on mass 1. We know that for mass 1 it's moving horizontally on the surface. We know that the normal force is just balanced vertically by the weight. So we can make that substitution minus mu m1g for the gravitational force here, balancing the normal force, and then the distance it's going to move is just going to be that distance h. So that is going to be the work done by the non-conservative force minus mu m1 gh. And that's going to equal to the final kinetic energy of both. Now, they are connected, so they're going to be moving at the same speed. So instead of writing two kinetic energy terms, we can just put one kinetic energy term 1/2 mv final squared, where the mass is just the sum of the two, because they're both going to have the same speed. So we can do it like this. Just move this a little bit. Plus m1 gy1 final. Right? So we're just writing it like this instead of writing the kinetic energy term twice, once for each mass. So we said that the gravitational potential energy of mass 1 is going to be the same initially and final. So we only have 3 terms left, and we have to solve for v final. Let's go ahead and do that. To solve for v final, we are going to take the square root after we divide everything by this, right? So we're going to have m2gh minus mu m1gh divide by all of this, the 1/2 m1 plus m2. That will give us v squared by itself, and now we just take the square root. Now we just plug in all of the values. m2 is 5 times 9.8, h is 1.5, mu is 0.4, m1 is 3, g is 9.8, h is 1.5, over 1/2 of 3 plus 5. Plug all of this in a calculator, and we will get that the final speed is equal to 3.74 meters per second. So I like this example just because it allows us to work with a system that consists of 2 masses and the Earth instead of just 1 mass. But you see that the equation works the exact same way.